I know. Now we have a sense of the beauty of black holes. Is there any astronomy to this? Do they exist? Can we see them? Well, technically, of course, we can't see them because no light gets out, besides which the star has not yet collapsed past its horizon. But black holes produce no light, so you can't actually see a black hole because they're black. What we can see is a very dense, massive object. So we can see, we need something to be orbiting it, something to be influenced, to be nearby, to be influenced by the intense gravity of a solar mass or 5 or 10 solar mass object, such that matter can orbit it within 300 kilometers. At that distance, you get very intense gravitational effects, and so if only something would orbit it, indeed, the way we discover black holes is when they are surrounded with something else, and for a stellar collapsed black hole, that typically requires that our star was part of a close binary so that there's stuff around from the other member of the binary, and the best way to have that happen is have a close binary with mass transfer. And when we have mass transfer, then the matter falling onto the black hole forms the usual accretion disk where it waits to lose its angular momentum to jets driven by magnetic fields in the disk in the standard way that we don't quite understand but have grown familiar to saying. The interesting thing is this disk extends all the way into 3 Schwarzschild radii, and there's nothing orbiting inside that because there are no stable orbits, but 3 Schwarzschild radii from a several solar mass black hole, that's extremely intense gravitational field, there's intense compression and heating, material is heated to millions of Kelvin, the radiation that it emits are X-rays, and so the way to detect black holes, at least initially, was to look for X-ray sources, and one of the first discovered, and the most famous, is Cygnus X1. You can guess what constellation that sits in. That's an X-ray binary, which is some X-ray source in close binary orbit with a type O supergiant. So we can see one star, and we can see from its spectrum that it's orbiting something, and there are X-ray flickers that are clearly too energetic, too hot, and also too rapid to be emitted from anything as large and flabby as a type O supergiant. And using the standard Doppler measurement technology, when you see a binary, spectroscopic binary, you can estimate the mass of this partner to the type O supergiant. And the mass estimates, depending on how it's done, it's not an easy business, come in between 10 and 20 solar masses, but there's at least 10 solar masses in this partner, so that's not very much for a star. Maybe there's some dim star there that we don't see, but how is a dim star producing so many X-rays? And, well, neutron stars produce X-rays, but a neutron star can't have a mass bigger than 2 or maybe optimistically 3 solar masses. What could produce X-rays and have 10 solar masses? Well, what nails it is that these X-ray signals are seen to flicker on very small time scales. It flickers in as little as a millisecond. Thousandth of a second is the time it takes these X-ray flickers to turn on and off. And that gives you a limit for the size of an object that can flicker in that time, because for some object to decide to turn on or off altogether takes at least as long as it takes for light to traverse the object from side to side, because no information can travel faster. So if something is flickering in a millisecond, it could not possibly be larger than 3,000 kilometers across. Now that's huge for a neutron star, but it's tiny for a star. You can't fit a star in 3,000 kilometers. You cannot even fit a good white dwarf in 3,000 kilometers. And something has 10 solar masses. The only option that we know is a black hole, and we have very good reason to believe that Cygnus and X1 and many X-ray sources that have been found since are in fact accretion disks around black holes. If there's a black hole around and nothing is falling on it, we really will not detect it. And so here is a nice recent Chandra Observatory X-ray image of Cygnus X1. So what we're seeing is not the blue supergiant, but the X-ray emissions from the accretion disk around the black hole, which is not resolved. We're not seeing a disk, we're just seeing the X-ray image. This is the X-ray spectrum by energy of the photons, and the peak is characteristic of ionized iron, and it's broadened by the, you would expect, intense pressures in the accretion disk around this very compact, massive object. And then for another astronomical fun black hole, this is a recently detected one in the Andromeda galaxy, and this is a black hole that has X-ray flares. Its disk is apparently undergoing violent changes, and periodically its X-ray luminosity increases. And for the first time, the radio image over here on the right is the contours in the middle are detecting for the first time the radio emission of gases compressed and heated and glowing by the collision of the polar jets that come out of this accretion disk, which we expect to happen when you have a black hole. So essentially, where black holes, stellar mass black holes, are not common because large stars, massive enough to produce the massive cores that collapse into black holes, are rare in the stellar population, but in a galaxy with 1 trillion stars, there's black holes all over the place. We see the ones that happen to have binary partners or some source for matter from which they are accreting, and as far as we know, there's no mass limit for a black hole. In fact, we see black holes with masses of 10, 5, 20, 100 solar masses, and then there's a gap, and then we see big holes with masses of millions up to billions of solar masses, and the issue of intermediate mass black holes, things that have masses between, say, 100 solar masses and 1 million solar masses, is a brand new thing. We think we have some recent discoveries, but people are still trying to understand where these objects come from. They certainly didn't start out as stars. Neither did these million solar massive black holes. Where do they live? Well, they live in the center of galaxies. The image over here on the right is a beautiful movie taken from images over a few years of the proper motions of stars near the center of the galaxy, near a famous X-ray source known as Sagittarius A star in the constellation Sagittarius, which is the direction to the center of the galaxy from us. And it's amazing. You can see stars far away from the center barely move, but the stars around the center are really whipping. You can use just their motion to measure, using Kepler's laws, the mass that the object they're orbiting, and you find some tens of millions or 10 million or a few million solar masses. The size of the object is limited, if only by the size of these orbits. It is clear that it is a very compact object. We also see jets and X-ray emissions from a big accretion disk around it. We are absolutely confident that at the center of the Milky Way galaxy sits a relatively minor
4 million solar mass
black hole. The black hole in the center of M31, the Andromeda galaxy, is probably 10 times at least more massive, and is more characteristic. Black holes of masses between 100 million up to 1 billion solar masses have been found and seem to be in the center of most massive galaxies. When we talk next week about galaxies, we'll ask the important question: does a black hole collect a galaxy around it, or does a galaxy produce a black hole? The answer to that, like many questions about galactic evolution, is maybe.